Right now, you're traveling through space at over 400,000 miles per hour, carried by a star racing around a supermassive black hole. That black hole sits at the center of our galaxy, the Milky Way, and it's 4 million times more massive than our Sun. Tonight, we'll take you on a journey from Earth to the edge of that cosmic monster, through stellar graveyards and gas clouds larger than entire solar systems, past stars being born and others being torn apart. If you're ready to see what our galaxy truly looks like, hit that like button and subscribe, because we're about to dive deep. Prepare yourselves. We begin. We start here on Earth, but our planet isn't sitting still. Right now, our entire solar system is hurtling through space at 67,000 miles per hour, faster than any rocket humans have ever built. You might think we're peacefully orbiting the Sun, but that's only part of the story. The Sun itself is dragging us along on a much wilder ride. Picture our solar system as a speedboat racing across an ocean. The Sun is the boat, and all the planets are passengers being pulled along for the journey. We're not drifting randomly through space. We're following a precise path around the center of our galaxy, completing one full orbit every 230 million years. The last time Earth was in this same position, dinosaurs didn't even exist. But here's where it gets strange. As we race around the galaxy, we're also moving up and down, like that speedboat bouncing over waves. Every 33 million years, our solar system passes through the flat disk of the Milky Way, then rises above it, and dips below it again. Some scientists believe these crossings might trigger mass extinctions on Earth. When we pass through the galactic disk, we encounter cosmic radiation, asteroid fields, and gravitational chaos. Think of it like driving through different neighborhoods in a massive city. Sometimes we're in quiet suburbs filled with empty space, and other times we're speeding through crowded downtown regions packed with stars, gas clouds, and cosmic debris. Right now, we're in one of those quieter neighborhoods. And that might be why life had a chance to develop on our planet. The strangest part is that we're not traveling alone. Our solar system sits inside a huge bubble of hot, thin gas that stretches for over 1,000 light years in every direction. This bubble was carved out by massive stars that exploded millions of years ago. Their blasts swept away most of the dense gas and dust, leaving us inside this relatively empty pocket of space. Without this protective bubble, Earth might look very different. Dense gas clouds and cosmic radiation could have made life far more difficult to survive. We're essentially living inside the aftermath of ancient stellar violence, cruising through a cavern hollowed out by star death. When we look up at the night sky, we're seeing the edges of this bubble in every direction. Most of the stars you see are on the far side of our cosmic neighborhood, shining through the thin walls of our protective shell. We're like passengers inside a glass submarine, drifting through the deep ocean of space. Our journey to the galactic center begins here, inside this quiet bubble of space. But as we move outward from our solar system, we'll discover that our peaceful neighborhood is surrounded by forces and structures that dwarf anything visible from Earth. The first of these cosmic landmarks lies just beyond our bubble, in regions where gas and dust begin to thicken, and new stars are born in spectacular fashion. This vast pocket of space has a name among astronomers, the local bubble. It stretches more than 1,000 light years across, and we're drifting through it like a speck of dust in a cathedral. But this cathedral was built through violence. Around 10 to 20 million years ago, a group of massive stars lived and died in this region. When stars more than 8 times heavier than our Sun reach the end of their lives, they don't fade quietly. They explode as supernovas, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. These explosions didn't happen just once. They occurred again and again as one massive star after another reached its violent end. Each supernova blast swept outward like an invisible tsunami, pushing gas and dust away from its core. When multiple supernovas erupt in the same region over millions of years, they merge together, forming what astronomers call a superbubble. Our local bubble is one of these cosmic hollows, still expanding outward from those ancient explosions. Imagine throwing stones into a calm pond, each one sending ripples that spread outward in perfect circles. Now picture throwing dozens of stones into the same spot again and again. The overlapping ripples would form a complex pattern of waves and calm patches. That's exactly what happened here, except instead of stones and water, we're talking about supernova explosions and the fabric of space itself. The walls of our bubble aren't empty. They're made of hot gas, heated to over 1 million degrees by those ancient stellar blasts. This gas is so thin that a cubic inch contains fewer atoms than the best vacuum ever created on Earth. Yet it glows faintly with X-ray light, invisible to our eyes, but easily detected by space telescopes. We're not sitting at the center of this bubble. Our solar system lies closer to one edge, slowly drifting toward a region where the bubble wall thickens with cooler gas and dust. In about 5 million years, we'll break through that wall and enter a denser region of the galaxy. When that happens, our solar system will face new challenges. The thin shell of hot gas around us acts like a protective shield, deflecting some of the cosmic radiation that would otherwise bombard Earth. Once we leave this protection and enter denser space, our planet's atmosphere will be hit by more high-energy particles from deep space. Some scientists even suggest this could lead to climate shifts or perhaps contribute to mass extinctions. For now, though, we continue sailing through this cosmic safe harbor, protected by the aftermath of ancient destruction. The irony is remarkable. The very explosions that once could have wiped out any life in this region now provide the shelter that allowed life to flourish on Earth, but our peaceful passage through the local bubble is about to lead us into something extraordinary. Just ahead, in the direction our solar system is moving, lie stellar nurseries, places where new stars are being born. Only about 400 light-years from Earth, something magnificent is happening in the darkness. Giant clouds of gas and dust are collapsing under their own gravity, and deep inside these cosmic cocoons, new stars are igniting for the very first time. The nearest of these stellar nurseries is so active that if our eyes could see infrared light, it would shine brighter than any star in the night sky. This region is known as the Orion Molecular Cloud Complex, a factory for creating suns. Imagine a cloud of gas and dust so vast that light takes several years to cross it. Now picture that cloud slowly contracting, like a giant hand squeezing a sponge. As it shrinks, it heats up, and when the center becomes hot enough, nuclear fusion ignites, and a new star is born. But star birth is never gentle. When a new star switches on, it unleashes powerful winds of charged particles, blasting through its surroundings at hundreds of miles per second. These stellar winds carve out bubbles and tunnels in the surrounding cloud, sculpting it into magnificent cosmic structures. Some newborn stars are so massive and energetic that they illuminate entire regions of their birth cloud, creating glowing nebulas visible across thousands of light years. The process of star formation takes millions of years, which might sound long, until you realize that most stars live for billions. It's like watching a flower bloom, except this flower is larger than our entire solar system and burns brighter than 1 million suns. Not every clump of gas becomes a star. Some collapse only part way, forming brown dwarfs, failed stars that glow dimly in infrared light. Others are torn apart by the intense winds and radiation from their more massive, successful neighbors. What makes this even more fascinating is that stars are not born alone. When a gas cloud collapses, it often fragments into dozens or even hundreds of pieces, each becoming its own star. These stellar siblings begin their lives together in tight clusters, sharing the same cosmic cradle. Over millions of years, they drift apart, pulled away by the gravity of the galaxy. Our own sun was born this way, in a cluster of thousands of stars about 4.5 billion years ago. Those long-lost siblings are now scattered throughout the Milky Way, impossible to identify, lost among hundreds of billions of stars. Somewhere out there, hidden in the vastness of space, are the brothers and sisters of our sun, stars that shared our origin, now shining alone in the galaxy. The formation of new stars in nearby regions offers a glimpse into our own origins. Every element in your body, except for hydrogen and helium, was created inside a star and scattered across space when that star died. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in stellar furnaces billions of years ago. You are, quite literally, made of star stuff, assembled from the ashes of ancient cosmic giants. These stellar nurseries mark only the beginning of our galactic journey. As we venture farther from Earth, we encounter the immense structure that contains these star-forming regions. Our solar system isn't floating in some random corner of the galaxy. It's woven into a vast structure known as the Orion Arm, or Local Arm, a minor spiral arm of the Milky Way that stretches thousands of light years in both directions from our position. Imagine the Milky Way as a massive hurricane viewed from above. The bright spiral arms seen in images are like storm bands, but instead of clouds, they're made of stars, gas, and dust. Most galaxies have 2 to 4 major spiral arms, with smaller ones branching off. The Orion arm is one of these smaller branches. For a long time, astronomers believed we lived in a short spur connecting 2 main arms, but new observations revealed something astonishing. The Orion arm is much larger and more significant than anyone thought, extending over 20,000 light-years. It's a major galactic feature, not a minor offshoot. We're not living in some cosmic backwater. We're part of a galactic superhighway. This spiral arm contains some of the brightest and most recognizable objects in the night sky: the stars of Orion, Perseus, and Cygnus, as well as many star-forming regions, including the molecular clouds we've already explored. The arm acts like a gravitational river, channeling gas and dust into dense regions where new stars are born. But spiral arms aren't permanent. They behave more like traffic jams in a cosmic highway. As material orbits the galaxy, it bunches up in certain regions, creating the illusion of spiral patterns. Stars and gas clouds flow into these arms, spend some time there, and eventually drift out again. Our solar system has likely passed through multiple spiral arms over its long orbit around the Milky Way. The difference in density between the arms and the spaces between them affects how often stars form. When clouds of gas enter an arm, they get compressed by stronger gravitational forces, triggering the birth of new stars. Massive stars that later explode as supernovas can either halt or spark even more star formation around them. Right now, our solar system sits about halfway between the galaxy's center and its outer edge, in what astronomers call the galactic habitable zone. This may not be a coincidence. Closer to the center, radiation and gravitational forces are too intense for stable planetary systems. Farther out, there aren't enough heavy elements to form rocky planets like Earth. Our place in the Orion arm is, quite literally, a cosmic sweet spot. As we continue our journey deeper into the galaxy, we'll leave our local arm behind and approach the massive structures that dominate the Milky Way's inner regions. But before we go further, consider this. You're not just sitting still right now. You're moving through space at unimaginable speeds. Earth spins on its axis at over 1,000 miles per hour at the equator. That's your first motion. Meanwhile, Earth orbits the Sun at 67,000 miles per hour, carrying you with it. But even that is nothing compared to the next layer. Our entire solar system is orbiting the center of the Milky Way at an incredible 514,000 miles per hour. Every second, you're traveling more than 140 miles through space, just from this galactic rotation. If you could step outside the galaxy and watch our solar system pass by, it would streak past you faster than your eyes could track. And that's still not the full story. The Milky Way itself is hurtling toward a massive galaxy cluster called the Virgo cluster at over 1 million miles per hour, which in turn is being pulled toward an even larger structure, the Great Attractor. Altogether, you're moving through the universe at roughly 1.5 million miles per hour. Think about that. In the time it took to read this sentence, you've traveled hundreds of miles through space and you didn't feel a thing. There's no wind, no acceleration, because everything around you is moving together. This immense galactic motion shapes more than just numbers. As our solar system orbits the Milky Way, it moves through different cosmic environments, sometimes passing through spiral arms filled with radiation and newborn stars, and other times drifting through calm, dark regions between them, like we are now. It takes our solar system about 230 million years to complete one full orbit around the galaxy, a galactic year. Since Earth formed, we've completed about 20 of these orbits. The last time we were in this exact position, life on Earth consisted of simple marine organisms. Dinosaurs, mammals, and humans, everything we know, evolved during our current lap around the Milky Way. The Milky Way doesn't rotate as a solid object. Stars closer to the galactic center orbit much faster, while those at the outer edges move more slowly. This differential rotation is what keeps the galaxy's beautiful spiral shape intact. If every part of the Milky Way spun at the same speed, its spiral arms would quickly wind up and vanish within a few 100 million years. As we travel closer toward the galactic core, these cosmic speeds grow even more extreme. and the effects of rotation give rise to some of the strangest and most fascinating phenomena in the universe. Between the bright stars that light our night sky lie the cosmic dead, remnants of ancient stars that burned out long ago. Scattered throughout our galactic neighborhood, these stellar corpses are invisible to the naked eye, yet they're all around us, and some rank among the most dangerous objects in existence. The most common of these are white dwarfs, the dense hot cores left behind when stars like our sun exhaust their fuel. A white dwarf can pack about 60% of the sun's mass into a sphere roughly the size of Earth. That means a single teaspoon of its material would weigh as much as a car. The nearest white dwarf lies just 8 to 12 light years away, making it one of our closest stellar neighbors. Newly formed white dwarfs blaze at temperatures over 100,000 degrees, but they gradually cool over billions of years. Some ancient ones have cooled so much that they're now colder than the sun's surface. Quiet, dim relics from the early universe, preserving a record of stars that died billions of years ago. Yet even in death, some white dwarfs can return to life in spectacular fashion. If one orbits close to a companion star, it can steal material from its partner through gravity. When enough of this stolen matter builds up, it ignites in a powerful thermonuclear explosion called a nova. The explosion blasts away the outer layers, and the process can repeat many times, a cosmic cycle of death and rebirth. Even stranger are neutron stars, the ultra-dense remnants left after massive stars, at least 8 times heavier than our sun, end their lives in supernova explosions. These are some of the most extreme objects in the universe. A single sugar cube-sized piece of neutron star matter would weigh 6 billion tons, more than Mount Everest. All that mass, greater than our sun's, is crushed into a sphere only about 12 miles, 20 kilometers, across. Some neutron stars spin hundreds of times per second, firing beams of radiation from their magnetic poles. When those beams sweep across Earth, we detect them as rhythmic pulses, giving these objects their name. Pulsars. Their precision rivals atomic clocks, with the fastest pulsar known rotating 716 times every second. The magnetic fields around neutron stars are trillions of times stronger than Earth's. If one were placed where the moon is, its magnetic power would erase every credit card on Earth. Get within 600 miles, 1,000-ton kilometers of a neutron star, and its magnetic field would instantly disrupt your nervous system. These stellar remnants aren't just cosmic oddities. They're natural laboratories for studying matter under conditions impossible to reproduce on Earth. Crushing gravity, extreme temperatures, and unimaginable magnetic fields. But these dead stars are only the beginning of what lies deeper within our galaxy. As we leave our familiar local arm and travel inward, we approach one of the Milky Way's grandest structures, the Perseus Arm. The Perseus Arm is one of the major spiral arms of the Milky Way, a colossal, star-packed superhighway filled with brilliant blue-white giants, dense gas clouds, and relentless cosmic activity. Moving from our quiet Orion Arm into the Perseus Arm is like stepping off a calm suburban street onto a roaring interstellar freeway. Here, stars can be 50 to 100 times more massive than the Sun, burning so intensely that they live only a few million years before collapsing or exploding as supernovas. The arm gets its name from the constellation Perseus, visible in the same direction from Earth. But the structure itself extends far beyond what we can see with the naked eye, stretching tens of thousands of light years around the galaxy, like a massive glowing spiral. If the Milky Way were the size of a dinner plate, the Perseus Arm would form one of the major glowing lines spiraling out from the center. So why are spiral arms like Perseus so active? It's because of the galaxy's density waves, patterns that bunch up gas and dust as they orbit, much like cars slowing in a traffic jam. When gas clouds hit these high-density zones, they get compressed, triggering bursts of star formation. As the clouds move out the other side, they spread again, but the newly born stars remain, lighting up the spiral arms we see across the galaxy. The Perseus Arm is home to some of the most breathtaking stellar nurseries in the known universe. One of the most iconic is the Eagle Nebula, famous for its towering pillars of creation, immense columns of gas and dust where new stars are being born. Each pillar stretches several light years high, sculpted by the intense radiation and stellar winds from nearby massive stars. Another dazzling region, the Rosette Nebula, glows in deep shades of red, the color of ionized hydrogen gas heated by a central cluster of young blazing stars. But the Perseus Arm isn't only about creation, it's also a stage for some of the universe's most violent endings. When those massive blue giants reach the end of their short, furious lives, they explode as supernovas, releasing energy equivalent to billions of suns. These explosions can be seen from galaxies millions of light years away, and though destructive, they also seed the cosmos, scattering heavy elements that will one day form new planets, moons, and even the ingredients for life itself. Traveling through the Perseus Arm would feel like passing through a cosmic construction zone. Everywhere you'd look, there would be motion and transformation. Stars being born, stars dying, gas clouds colliding, and radiation blazing across the darkness. It's a region of breathtaking beauty and deadly intensity. As we move closer to the galactic center, the scale of what we encounter grows even more mind-bending. Imagine looking up at a night sky where the stars are so densely packed they blur together into glowing clouds. Here we find stellar clusters, immense cities of stars, each containing hundreds of thousands, even millions of suns, all born from the same primordial nebula. The most massive and ancient of these are globular clusters, vast, spherical collections of stars formed over 12 billion years ago, when the universe itself was young. A single globular cluster can hold 1 million stars packed into a sphere only a few hundred light years wide. If Earth orbited a star near the center of one, our night sky would never be dark. Thousands of stars would shine brighter than Venus, filling the heavens with a golden twilight. In our part of the galaxy, the nearest star lies over 4 light years away. But in a globular cluster's core, stars can sit closer together than the planets in our solar system. If the Sun existed in such a region, dozens of other stars might be visible from Earth, closer than Pluto's orbit. These environments would be chaotic. Gravitational tugs between neighboring stars would make planetary orbits wildly unstable. Worlds could be flung into interstellar space or smashed into their parent suns, but not all stellar clusters are ancient. Scattered across the Milky Way's disk are open clusters, groups of young stars that formed more recently from the same cloud of gas and dust. The most famous example is the Pleiades, or Seven Sisters, visible to the naked eye. This open cluster contains over 1,000 stars, all born within the last 100 million years. Unlike their ancient cousins, many open clusters are still wrapped in the gas and dust that gave them life. Within these glowing clouds, astronomers can watch new stars ignite in real time, while others are still forming. It's like seeing a cosmic city under construction. Over time, however, open clusters begin to dissolve. Gravitational encounters with nearby stars and gas clouds gradually tear them apart. Within 1 billion years, most scatter completely, their stars drifting off to become solitary travelers, just like our own sun once did. Because all stars in a cluster formed at the same time and from the same material, these clusters serve as natural laboratories for studying stellar evolution. Astronomers can directly compare how stars of different masses live, age, and die, side by side under nearly identical conditions. Some of the galaxy's youngest and most intense clusters are known as superstar clusters, regions so dense with giant stars that dozens of them, each 50 times more massive than the Sun, can fit into a space smaller than our solar system. Their radiation and stellar winds are ferocious, shaping their surroundings with incredible power. But even these cosmic metropolises are just a preview of what lies ahead. Between the stars flows an invisible ocean, the interstellar medium. Though space seems empty, it's actually filled with vast currents of gas and dust, flowing like rivers between the spiral arms of the galaxy. These interstellar streams are invisible to our eyes, yet they sculpt the Milky Way's evolution, carrying the raw material for star formation across cosmic distances. They don't flow randomly. Guided by the galaxy's rotation and gravity, they form long filaments stretching thousands of light years through space. Imagine stirring honey into coffee. The swirling motion creates spiraling patterns, just like the Milky Way's rotating gas. The composition of these cosmic rivers tells the story of life and death across the galaxy. Most of the gas is hydrogen and helium left over from the Big Bang, but mixed in are heavier elements: carbon, oxygen, silicon, iron, and more. Forged in the hearts of ancient stars and spread by supernova explosions. These enriched flows circulate throughout the Milky Way. Some streams spiral inward, feeding the star factories near the galactic core, while others drift outward, carrying the ashes of dead stars to the galaxy's quieter outskirts, including the region where our solar system resides. Over billions of years, this circulation has gradually redistributed the ingredients for planets and life itself. But these flows are anything but calm. The interstellar medium is turbulent and violent, stirred constantly by stellar winds, supernova shockwaves, and gravitational forces. A single supernova's shockwave can compress a nearby gas cloud, triggering the birth of new stars. Or it can tear one apart, halting star formation entirely. Through this endless cycle of destruction and renewal, the Milky Way continues to evolve, a living, breathing galaxy, shaped by both chaos and creation. Temperature variations within these vast gas streams create a rich and complex ecosystem of interstellar environments. Some regions contain hot, diffuse gas heated to millions of degrees by powerful supernova explosions, while others harbor cold, dense molecular clouds where temperatures fall to just a few degrees above absolute zero. These frigid molecular clouds serve as the nurseries for new stars, though they make up only a small fraction of the total interstellar volume. Threaded through these gas streams are faint magnetic fields that add yet another layer of complexity. Although incredibly weak compared to those on Earth, these fields guide the motion of charged particles and influence how gas clouds collapse to form stars. They also accelerate cosmic rays, high-energy particles that race across the galaxy at nearly the speed of light. As our journey brings us closer to the galactic center, these interstellar rivers grow increasingly turbulent and energetic. Gas densities rise, magnetic fields strengthen, and the pace of star formation accelerates dramatically. We're approaching the regions where the calm, relatively quiet interstellar medium of our local space gives way to the chaotic heart of the Milky Way. The next great structure we encounter marks a dramatic leap in both scale and intensity, the Scutum Centaurus arm, the longest and most massive spiral arm in our galaxy. This colossal formation wraps more than halfway around the Milky Way, serving as a kind of superhighway for star formation and stellar activity. It takes its name from the constellations Scutum and Centaurus, tiny patches of sky that barely hint at its true grandeur. The Scutum Centaurus arm stretches for over 60,000 light-years, longer than the distance from Earth to the galactic center, and contains some of the most active star-forming regions known. What makes this arm unique is its proximity to the galactic core. As one of the inner spiral arms, it continuously receives fresh infusions of gas and dust from the central regions. This material flows along the arm like a conveyor belt, creating a nearly unbroken chain of stellar nurseries and massive star clusters, a cosmic assembly line for stars. The rate of star formation here is astonishing. In some sectors, new stars are born thousands of times faster than in our relatively peaceful neighborhood. And these aren't ordinary stars. The arm specializes in producing stellar giants, 50 to 100 times more massive than our Sun. When these titans reach the end of their lives and explode as supernovas, they can outshine entire galaxies for weeks. One of the arm's most striking features is the Scutum star cloud, visible to the naked eye as a bright patch within the constellation Scutum. This region is packed with some of the most luminous stars ever observed, including red supergiants so enormous they could engulf the orbit of Mars if placed at the center of our solar system. These massive stars burn through their nuclear fuel at breakneck speed, living only a few million years before collapsing in violent explosions. The dense environment of the Scutum Centaurus arm creates a gravitational playground where massive stars and clusters interact in dynamic and unpredictable ways. Some stars are flung from their birthplaces at tremendous speeds, becoming runaway stars that streak across the galaxy. A few move so fast they will one day escape the Milky Way entirely, drifting through intergalactic space as solitary wanderers. Perhaps the most extraordinary role of this arm, however, is its function as a galactic highway feeding the core. Gas and dust flowing along its length are gradually funneled inward, fueling the turbulent regions surrounding the galaxy's heart. For billions of years, this process has helped shape and sustain the massive central structures of the Milky Way. Following these currents deeper into the galaxy, we approach a domain where gravity dominates and the familiar rules of stellar physics begin to fail. Here, matter is compressed and distorted under immense forces, behaving in ways that defy ordinary understanding. The next structure we encounter reveals one of the Milky Way's greatest secrets, its hidden backbone. At the very center of our galaxy lies a vast bar-shaped structure made of stars and gas. the galactic bar. Though invisible from Earth's vantage point, it is larger than anything we've encountered so far and serves as the dynamic core that governs the flow of matter across the Milky Way. If you could view our galaxy from above, instead of a simple spiral pattern, you'd see a cosmic barbell, a bright, elongated bar stretching over 27,000 light-years, roughly half the diameter of the entire galactic disk. This immense structure rotates as a single unit, spinning faster than the surrounding spiral arms. The galactic bar formed billions of years ago through a process known as bar instability. As the Milky Way matured and stars settled into circular orbits, subtle gravitational interactions gradually produced elongated streams of stars. Over hundreds of millions of years, these patterns strengthened and merged, eventually solidifying into the magnificent bar we observe today, the gravitational backbone of our galaxy. About 2/3 of all spiral galaxies contain central bars similar to our own, but the Milky Way's bar is far from a static feature. It acts as a cosmic pump, channeling gas from the galaxy's outer regions toward its core through a process known as gravitational torquing. As vast gas clouds orbit the Milky Way, they encounter the bar's powerful gravitational field, which diverts them from circular paths into elongated orbits that spiral inward, much like water swirling down a drain. The difference is, this drain stretches 27,000 light-years across. This continuous inward flow of material has shaped the Milky Way for billions of years. The bar has been feeding gas and dust into the galactic center, building up the dense star clusters and massive structures found there today. Without this gravitational pump, the galactic core would be a much quieter, less active region. The bar's influence also extends to the motion of stars throughout the galaxy. Any star that drifts too close can be gravitationally scattered onto a new trajectory. Some are flung toward the galactic center, while others are sent outward to the edges of the Milky Way. Even our solar system may have crossed paths with this influence during its long orbit around the galaxy, though we currently reside well beyond its direct reach. Recent observations reveal that the galactic bar isn't smooth or uniform. It contains its own subtle spiral structure, dense lanes of gas and dust wrapped around its length like strands of cosmic DNA. These inner spirals are hotspots of intense star formation, fueled by the steady inflow of fresh material from the outer galaxy. The bar's rotation is finely tuned to maintain the Milky Way's spiral shape. If it rotated even slightly faster or slower, the galaxy's spiral arms would either wind up too tightly or unravel completely within a few 100 million years. This delicate balance has preserved the Milky Way's overall form for billions of years. As we move along the bar toward the galactic center, the density of stars and gas rises sharply. Space itself begins to change. The empty stretches between stars give way to vast molecular clouds so massive they dwarf entire solar systems. These are the galaxy's industrial zones, where star formation occurs on an unimaginable scale. The largest of these, Sagittarius B2, lies just 300 light-years from the galactic center. This single molecular cloud contains enough raw material to create 3 million suns. To put it in perspective, if our solar system were shrunk to the size of a marble, Sagittarius B2 would still be larger than a football stadium. Its immense gravity even influences the orbits of nearby stars. Inside these clouds, conditions are extreme. Temperatures drop to just 10 degrees above absolute zero, forming dense fogs of molecular hydrogen. Within this icy environment, chemistry thrives. Over 150 different molecules have been detected, ranging from simple compounds like water and carbon monoxide to complex organic molecules that could serve as precursors to life. Some clouds even contain vast quantities of ethyl alcohol, enough to fill Earth's oceans, and others harbor molecules that would smell like raspberries or taste like rum. But these molecular giants are anything but calm. They are constantly stirred by radiation from nearby stars, shockwaves from supernovas, and tangled magnetic fields. The result is a dynamic internal landscape, with dense cores, expanding shells, and turbulent flows of gas, resembling colossal cosmic weather systems complete with their own storms and circulation. When certain regions within a cloud become dense enough, gravity begins to take over. The collapse happens unevenly. Some areas fall inward faster than others, sparking a cascade of star formation that can last for millions of years. The most massive sections collapse first, giving birth to giant stars that will eventually explode as supernovas, triggering new waves of collapse in nearby regions. The scale of creation here is staggering. A single molecular complex can form thousands of stars at once, producing massive stellar clusters that outshine entire galaxies. These are some of the brightest star-forming regions in the known universe, driven by the powerful molecular clouds that cluster near galactic centers. As we venture deeper into the Milky Way's heart, these clouds grow even more extreme. Gas densities climb, gravitational forces intensify, and the rate of star formation soars to levels that would sterilize any nearby planets with intense radiation. We're now entering the central molecular zone, the most violent, energetic, and mysterious region in our galaxy. This vast ring of molecular clouds, about 1,000 light-years wide, encircles the Milky Way's supermassive black hole. Despite occupying less than 1% of the galactic disk's area, it holds as much gas and dust as the entire inner galaxy combined, enough to build 10 million suns. If our region of space has the density of air, the central molecular zone has the density of water, yet, paradoxically, it forms far fewer stars than expected, 10 to 100 times fewer in fact. Something here is suppressing star formation, and astronomers are still uncovering why. The key lies in the extreme conditions near the galactic core. Powerful magnetic fields, energized by both the supermassive black hole and countless massive stars, thread through the clouds like invisible steel cables, holding them up against gravitational collapse. This tension prevents new stars from forming as easily as elsewhere in the galaxy. When star formation does break through these forces, it gives rise to some of the most massive stars ever seen, titans over 100 times the mass of our Sun, glowing blue-white even from thousands of light-years away. They burn furiously and die quickly, often exploding as supernovas after just a few million years. Here, temperatures tell the story of cosmic violence. While the cloud cores remain icy cold, the space between them blazes with gas heated to millions of degrees, energized by shockwaves from stellar explosions and the fierce radiation of the central black hole. Welcome to the central molecular zone, the most extreme and awe-inspiring neighborhood in our galaxy, where the forces of creation and destruction exist side by side, shaping the Milky Way from within. This creates a strange environment where freezing cold molecular gas exists just a few light-years away from plasma so hot that it can strip electrons from atoms. Magnetic field strengths here are thousands of times greater than anything found in our solar neighborhood. These fields accelerate particles to incredible speeds, producing streams of cosmic rays that race throughout the galaxy. Some of these high-energy particles eventually reach Earth, where they're detected by cosmic ray observatories as showers of subatomic particles in our atmosphere. The central molecular zone acts as a massive reservoir, storing gas and dust that occasionally get funneled even closer to the galactic center. When gravitational instabilities or stellar explosions disturb this delicate balance, streams of material spiral inward toward the supermassive black hole, triggering bursts of activity visible across the electromagnetic spectrum. As we move deeper into this cosmic storm, we approach the point of no return. At the very heart of our galaxy, something is broadcasting. Radio telescopes on Earth detect a constant stream of signals coming from the galactic center, electromagnetic messages carrying information about conditions no human could ever experience firsthand. These radio waves have traveled 26,000 light-years to reach us, bringing news from the most violent place in our cosmic neighborhood. The signals tell a story of chaos. Unlike the steady radio emissions from ordinary stars, the galactic center broadcasts in bursts and flares that can vary in intensity within minutes. Sometimes the signal strength increases by hundreds or even thousands of times before fading back to normal. These fluctuations are the radio signatures of matter falling into our galaxy's central black hole, emitting its final electromagnetic cry before vanishing forever. But the central black hole isn't the only radio source in this dense region. Scattered throughout the galactic center are dozens of compact radio sources, cosmic lighthouses beaming energy in all directions. Some are neutron stars, the ultra-dense remnants of massive stellar explosions. Others are stellar mass black holes, smaller cousins of the central giant, actively feeding on nearby gas and dust. The most mysterious radio signals come from long, thin structures called non-thermal filaments. These cosmic threads stretch for hundreds of light years through the galactic center, glowing brightly in radio wavelengths, yet remaining completely invisible to optical telescopes. Scientists believe they're illuminated by high-energy electrons spiraling through powerful magnetic fields, though their true nature remains one of astronomy's unsolved puzzles. Radio observations have also uncovered the skeletal structure of gas flows near the galactic center. Hot, ionized gas streams spiral inward toward the black hole, forming curved radio arcs that trace the influence of its immense gravity. These gas streams don't fall straight in. Instead, they follow complex orbital paths, sometimes circling the black hole multiple times before finally crossing the point of no return. One of the most dramatic discoveries was the observation of massive gas clouds being torn apart by the black hole's gravity. Astronomers watched in real time as a cloud called G2, containing about 3 times Earth's mass, stretched into a long stream as it neared the black hole. The radio emissions captured the cloud's destruction over several years, offering a direct glimpse of gravitational violence on a cosmic scale. The radio waves also reveal a hot, thin atmosphere surrounding the galactic center, gas heated to millions of degrees by shock waves from stellar explosions and energy released by the black hole itself. These emissions form a glowing halo around the galaxy's core, visible only to radio telescopes. Perhaps most astonishingly, radio observations have detected relativistic jets erupting from the galactic center. These are narrow beams of matter and energy, traveling nearly at the speed of light. Blasted outward by magnetic fields near the black hole, the jets extend for thousands of light years above and below the galactic plane, carrying energy and particles far from their origin point. These radio signals are our only window through the thick dust and gas that obscure the galactic center from optical view, revealing a glimpse into the most extreme physics. Laboratory in the Milky Way, at the very core of our galaxy, within a space smaller than the distance from Earth to our nearest stellar neighbor, reside over 25 million stars. This is the nuclear star cluster, the densest stellar region in the Milky Way, and one of the most crowded places in the known universe. If our solar system were located here, the night sky would shine with thousands of stars brighter than our full moon. The density of stars here defies imagination. While the nearest star to our sun is over 4 light years away, stars in the nuclear cluster can be separated by distances smaller than our solar system itself. In the very center, neighboring stars might be only a few billion miles apart, close enough for their outer layers to interact during close passes. Planetary systems couldn't survive here. The gravitational chaos would tear apart any orbits within mere thousands of years, and these aren't ordinary stars. Many are stellar exotics, objects that form only under the most extreme conditions. Wolf-Rayet stars burn so intensely that they eject their outer layers in powerful stellar winds moving thousands of miles per second. Red supergiants expand to sizes larger than Earth's orbit around the Sun. Blue hypergiants blaze with the brightness of millions of suns, burning through their nuclear fuel so quickly they explode after only a few million years. Gravity here operates by different rules. Stars don't follow simple elliptical orbits like planets around the Sun. Instead, they trace intricate rosette-shaped paths pulled by the combined gravity of millions of nearby stars and the central black hole. Some follow highly elongated orbits, swinging from the cluster's edge almost to the black hole's event horizon, before looping back again. This cluster took billions of years to form. As gas spiraled inward toward the galactic center, bursts of star formation were triggered near the supermassive black hole. Over time, generations of these stars built up the massive structure we see today. But this didn't happen gradually. It occurred in violent bursts, each triggered by major infall events, producing distinct populations of stars with different ages and compositions. Life cycles here are fast and furious. Massive stars form, live, and die within just a few million years, their supernova explosions adding to the surrounding chaos. The cluster contains dozens of stellar mass black holes, neutron stars, and white dwarfs, all packed into the same small region as the living stars. When these compact remnants interact, they can merge and create gravitational waves that ripple across the universe. The nuclear cluster even acts like a natural particle accelerator, using gravitational slingshot effects to hurl stars at extreme speeds. Some are ejected at over 1,000 miles per second, fast enough to escape the Milky Way entirely. These hypervelocity stars have been detected speeding through the outer galaxy, refugees from the gravitational violence at its core. And at the very heart of all this chaos lies the source: our galaxy's supermassive black hole, Sagittarius A. This cosmic monster, sitting perfectly still at the Milky Way's gravitational center, contains the mass of 4 million suns compressed into a space smaller than Mercury's orbit. It's the anchor that holds our entire galaxy together. For decades, astronomers suspected its existence but couldn't prove it. The galactic center is hidden behind vast clouds of dust that block visible light. But in the 1990s, infrared telescopes that could peer through the dust began tracking individual stars near the center. What they discovered revolutionized our understanding of black holes. The stars closest to Sagittarius A follow elliptical orbits so extreme they test the limits of physics. One star, designated S2, completes a full orbit around the black hole every 16 years, racing through space at astonishing speeds as it dances with the darkness. At its closest approach, the star races past the black hole at over 25 million miles per hour, fast enough to cross the distance from Earth to the Moon in just 30 minutes. The gravitational forces at this proximity are so intense that they create measurable effects predicted by Einstein's theory of relativity. But Sagittarius A is not a quiet monster. Though it appears calm most of the time, the black hole occasionally flares with violent bursts of activity whenever gas or debris drifts too close. During these feeding events, its brightness can increase by factors of hundreds within minutes as matter spirals inward, heating to billions of degrees before vanishing forever. The energy released during such flares can outshine all the stars in the nuclear cluster combined. The black hole's event horizon, the boundary beyond which nothing can escape, has a diameter of about 15 million miles. Though that might sound large, it's tiny compared to its sphere of influence, which extends for several light years in all directions. Within this region, the black hole's gravity dominates completely, controlling the movement of stars, gas clouds, and even light itself. Perhaps the most remarkable discovery about Sagittarius A came in recent years when astronomers captured the first direct image of its shadow. Using a planet-sized network of radio telescopes working together, they photographed the dark silhouette of the event horizon surrounded by a glowing ring of superheated gas. The image confirmed decades of theoretical predictions about what a black hole should look like. The magnetic field around Sagittarius A is millions of times stronger than Earth's magnetic field. This immense magnetism accelerates particles to nearly the speed of light, launching them in narrow jets that extend thousands of light years above and below the galactic plane. These jets carry energy and matter far from the black hole, influencing star formation and gas dynamics throughout the Milky Way. Every star in our galaxy, including our Sun, is ultimately orbiting this central giant. Even though we're 26,000 light years away, Sagittarius A's gravity still guides our motion through space. The event horizon represents the ultimate frontier, where space and time themselves begin to break down. It's the edge of everything. This boundary marks the point where the normal laws of physics surrender to something far stranger. Cross this invisible line, and you enter a region from which nothing, not matter, light, or even information, can ever return. It's the ultimate point of no return, a one-way barrier between our universe and whatever lies beyond. The event horizon isn't a physical surface you could touch. It's a mathematical boundary defined by gravity so intense that the escape velocity exceeds the speed of light. Since nothing can move faster than light, nothing can escape once it crosses that line. The horizon forms a perfect sphere surrounding the black hole, roughly 15 million miles in diameter, large enough to contain the orbits of Mercury and Venus if the black hole sat where our Sun is. Here's where things get strange. If you approach the event horizon, your experience would depend entirely on your perspective. To a distant observer watching your fall, you would appear to slow down as you neared the horizon. Your image would redshift to longer and longer wavelengths until you faded from view, seemingly frozen at the edge forever. Time dilation would stretch your final moments into eternity from their point of view. From your own perspective, however, the experience would be very different. You'd pass through the event horizon without any noticeable change, no boundary, no sudden shift. You might not even realize you had crossed it until you tried to turn around and found that every direction now led deeper toward the black hole's center. The horizon would be invisible, just empty space with a special property. The space near the event horizon warps in ways that defy ordinary understanding. Tidal forces become so extreme that they would stretch and tear any object that ventured too close. A process astronomers call spaghettification. Your feet would experience much stronger gravity than your head, stretching you into a long, thin shape before tearing you apart atom by atom. Time also behaves differently near the event horizon. The intense gravitational field causes time to run slower compared to regions farther away. A clock at the horizon would tick at a different rate than one in normal space. This phenomenon, known as gravitational time dilation, means the black hole exists in a different frame of time than the rest of the galaxy. The horizon marks the boundary where space-time curvature becomes infinite. At the very center lies the singularity, a point where density becomes infinite and the known laws of physics collapse entirely. The event horizon shields the rest of the universe from this cosmic paradox. Recent theories, however, suggest that black hole event horizons may not be as absolute as once believed. Quantum effects near the boundary could allow tiny amounts of information to escape through a process known as Hawking radiation. But these effects are so weak that they're undetectable for supermassive black holes, like Sagittarius A. Beyond the event horizon lies territory that challenges the very foundations of reality. From the Milky Way's central black hole, two invisible spheres of energy pierce through space at 99% the speed of light. These relativistic jets extend thousands of light years above and below the galactic plane, carrying matter and energy far from the black hole's grasp in one of the most spectacular demonstrations of cosmic power in the universe. What makes these jets even more extraordinary is that they originate from something that supposedly allows nothing to escape. The jets don't come from inside the black hole itself, but from the swirling disk of superheated gas and plasma spiraling toward it. As this material falls inward, it becomes compressed and heated to billions of degrees, creating conditions far more extreme than the core of any star. The magnetic fields threading through this accretion disk twist and intensify until they are powerful enough to launch streams of particles at relativistic speeds. Imagine these magnetic field lines as rubber bands wound tighter and tighter. Eventually, they snap back with tremendous force, accelerating charged particles along narrow channels that extend far from the black hole. These jets remain astonishingly focused, maintaining their precision over thousands of light years, a level of stability no human technology could ever achieve. The jets from Sagittarius A are relatively weak compared to those from more active supermassive black holes in other galaxies. Some galactic jets are so powerful they can be detected from billions of light years away, outshining all the stars in their host galaxies combined. Our galaxy's central black hole is currently in a quiet phase, producing jets so faint they are barely detectable even with our most sensitive instruments. Yet even these weaker jets carry enormous energy. The particles streaming through them are accelerated to energies millions of times higher than anything achievable in human-built particle accelerators. When these high-energy particles interact with magnetic fields or matter along their path, they emit gamma rays, the most energetic form of electromagnetic radiation in the universe. These jets act as cosmic particle accelerators, producing some of the highest energy cosmic rays that bombard Earth's atmosphere. These particles travel so fast that time dilation becomes significant. From their own perspective, their journey across the galaxy might take only minutes or hours, while thousands of years pass for us. Recent observations have shown that the jets from Sagittarius A change direction over time. The black hole's rotation axis doesn't always point the same way, causing the jets to wobble like water from a spinning sprinkler. This slow procession unfolds over thousands of years, gradually sweeping the jets across different parts of the galaxy. As the jets interact with the surrounding interstellar medium, they generate shock waves that heat the gas clouds they encounter. This process helps regulate star formation, injecting energy into molecular clouds that might otherwise collapse to form new stars. These relativistic beacons represent the black hole's most visible influence on the Milky Way, extending its reach far beyond the gravitational prison of the event horizon. Near the supermassive black hole at our galaxy's center, time itself becomes a variable. The immense gravitational field warps the fabric of space-time so severely that clocks run slower, distances stretch, and reality itself bends in ways that would seem impossible anywhere else in the universe. Welcome to the realm where Einstein's wildest theories become everyday physics. This phenomenon, known as gravitational time dilation, means that time passes differently depending on how close you are to the black hole. A clock placed just outside the event horizon would tick far slower than one in normal space. From our vantage point on Earth, 26,000 light-years away, that clock would appear almost frozen, its hands barely moving as gravity stretches each second into an eternity. The effect is not subtle. Near Sagittarius A, time dilation becomes effectively infinite from an outside observer's perspective. Anything falling toward the black hole would appear to slow dramatically as it approached the horizon, its image redshifting and fading until it vanished, seemingly frozen at the edge of forever. But this warping of time extends well beyond the event horizon. Stars orbiting close to the black hole experience measurable time dilation. The star S2, which orbits Sagittarius A every 16 years, actually ages slightly slower than it would if it orbited farther away. Over millions of years, that difference could amount to thousands of extra years in its stellar lifetime. The bending of time is deeply tied to the curvature of space. Near the black hole, space itself curves like a bowling ball pressing into a rubber sheet. This curvature affects not just how time flows, but also how light and matter move. What would normally be straight paths become curved trajectories near the black hole. One of the most mind-bending consequences of this warped geometry is the theoretical existence of closed time-like curves. In certain regions near rotating black holes, space-time can loop back on itself, making time travel into the past theoretically possible. However, these exotic paths exist only under the most extreme conditions and would destroy any known form of matter long before such travel could occur. The effects of time dilation near Sagittarius A also influence the light we observe from that region. Radio signals from gas clouds spiraling into the black hole reach Earth with their frequencies shifted by gravity, a phenomenon called gravitational redshift. This redshift gives astronomers direct measurements of the black hole's mass and the strength of its gravitational field. Perhaps most astonishingly, the time warping around supermassive black holes may help explain some of the greatest mysteries in cosmology. Some theories propose that the extreme curvature of space-time near black holes could be connected to the expansion of the universe itself, linking the smallest and largest scales of cosmic physics. As we pull back from this region, where time itself bends and breaks, we begin to see how our entire galaxy is embedded within something far larger and even more mysterious. Surrounding the Milky Way's visible stars and gas clouds lies a massive, spherical halo of dark matter, a substance that outweighs all visible matter by a ratio of 10:1. This invisible halo extends far beyond the spiral arms, forming a hidden architecture that holds our galaxy together and determines how it moves through the universe. Dark matter neither emits, absorbs, nor reflects light of any kind. It is completely invisible across the electromagnetic spectrum, from radio waves to gamma rays. The only evidence of its existence comes from its gravitational effects on visible matter. Stars in the outer regions of galaxies orbit faster than they should if only visible mass were present. Something with tremendous gravitational pull must be holding them in place. The Milky Way's dark halo is immense, stretching at least 600,000 light-years from the galactic center, about 3 times larger than the visible galaxy itself, and large enough to encompass several of our satellite galaxies. If we could somehow see dark matter, the Milky Way would appear as a small bright disk floating in the center of a vast, faintly glowing sphere. This invisible halo holds nearly 1 trillion solar masses of dark matter, making it the most massive part of our entire galaxy. Everything we can see, the stars, planets, dust, and gas, makes up only about 15% of the Milky Way's total mass. In truth, we're living inside a vast cloud of dark matter, with normal matter sprinkled on top like seasoning on a cosmic dish. But this dark halo isn't smooth. Simulations reveal that it's filled with clumps and streams of dark matter flowing through space. Some of these may be the remains of small galaxies that the Milky Way tore apart billions of years ago, while others could be primordial structures from the dawn of the universe that still exist today. The nature of dark matter is one of science's greatest mysteries. It may be made of exotic particles that barely interact with ordinary matter, making them nearly impossible to detect. Despite massive experiments worldwide, dark matter has lived up to its name, remaining invisible and elusive. This halo played a crucial role in the birth of our galaxy. Early in the universe, dark matter clumped first, creating gravitational wells that pulled in gas and dust. Without this unseen framework, galaxies like the Milky Way could never have formed. As our solar system moves through the halo, we're actually passing through a cosmic wind of dark matter particles streaming by at hundreds of kilometers per second, completely undetectable, yet constantly surrounding us. Beyond this halo lies an even grander cosmic landscape. The Milky Way is not alone. It's surrounded by dozens of smaller galaxies, like moons orbiting a planet. These satellite galaxies vary from tiny clusters of stars to full stellar systems containing billions of suns. Together, they form a dynamic gravitational ecosystem, constantly changing over billions of years. The most famous companions are the large and small Magellanic Clouds, visible from the southern hemisphere as faint glowing patches. The large cloud hosts about 30 billion stars, while its smaller partner holds around 3 billion. But these are just the brightest. Astronomers have found over 50 smaller satellites orbiting our galaxy, with names like Draco, Ursa Minor, and Sagittarius. Some lie just 75,000 light-years away, while others orbit as far as 3 million light-years from the galactic center. The Milky Way's gravity tears many of them apart, leaving long streams of stars scattered across the sky. The Sagittarius dwarf galaxy is one such victim, currently being shredded and absorbed into the Milky Way's outer regions. Interestingly, many of these satellites are rich in dark matter, with their visible stars accounting for only a fraction of their true mass. Some are so dominated by dark matter that they exist as ghost galaxies, barely visible, held together by gravity alone. Even their arrangement challenges our expectations. Instead of being scattered randomly, these galaxies are aligned in a flattened, disk-like structure, hinting that the early universe was more organized than once believed. Trailing behind the Magellanic Clouds is one of the largest features in our sky, the Magellanic Stream, a colossal river of hydrogen gas stretching over 600,000 light-years. This stream tells the story of a slow-motion galactic collision, where the Milky Way's gravity is stealing gas and stars from its companions. The stream isn't just one trail, it's a complex network of gas filaments flowing both toward and away from our galaxy. The gravitational tug-of-war between the two Magellanic Clouds adds to this chaos, producing structures that contain enough gas to form 2 billion new stars. As this material eventually falls into the Milky Way, it will ignite new waves of star formation, keeping our galaxy alive for billions of years more. What's more, the gas in this stream is chemically primitive. It has fewer heavy elements than our own galactic material. When it mixes in, it refreshes the Milky Way's fuel, allowing stars to keep forming long after most galaxies would fade. Even dark matter is part of the story. The Magellanic Stream contains dark matter stripped from its parent galaxies, helping to shape its path and stability. By studying this stream, astronomers can map the Milky Way's mass and gain clues about dark matter's true nature. The Magellanic Stream is just one of many cosmic scars left by past mergers. Across the sky, countless faint streams mark the remains of galaxies that the Milky Way has already consumed, reminders that galaxy formation never truly ends. Yet all of this is only a prelude, because in about 4.5 billion years, an even more dramatic event awaits us, a cosmic collision that will transform our night sky forever. The Andromeda galaxy, our nearest large neighbor, is hurtling toward us at an incredible 250,000 miles per hour. In about 4.5 billion years, it will collide with the Milky Way in one of the most spectacular cosmic events our galaxy will ever experience. This collision will completely reshape both galaxies, flinging countless stars into new orbits and sparking one of the largest bursts of star formation in galactic history. But despite the word collision, almost no stars will actually crash into each other. The distances between them are so immense that most will simply pass by unscathed. Instead, it will be a collision of gravity, gas clouds, and dark matter halos, an immense gravitational dance that will transform both galaxies over hundreds of millions of years. Andromeda, home to nearly 1 trillion stars, is far larger than our Milky Way, which has about 400 billion. And because Andromeda is heading toward us almost head-on, the encounter will be even more dramatic than a glancing. Past computer simulations show that the first close approach will tear out massive tidal tails, streams, of stars stretching hundreds of thousands of light-years into space. In the chaos, the supermassive black holes at the centers of both galaxies will spiral toward each other, generating gravitational waves that ripple through space-time itself. When they finally merge, they'll unleash more energy through those ripples than all the stars in both galaxies emit in light. Our solar system will likely survive this event, but its position will change dramatically. The Sun and its planets could be flung toward the outer edges of the new galaxy or drawn closer to its new center. By that time, however, the Sun will be entering its red giant phase, and Earth's habitability will already be long gone. As the two galaxies merge, gas clouds will collide and compress, triggering massive waves of new star formation. For a time, the sky will blaze with the light of billions of newborn stars, making the merged system one of the brightest galaxies in the universe. Astronomers estimate the rate of star formation could increase by hundreds of times compared to today. The merged galaxy even has a name, Milky, a vast, elliptical galaxy formed when the graceful spiral arms of both galaxies are destroyed. It will be larger, denser, and more massive than either of its parents, containing the combined stars, gas, and dark matter of both. But even this cosmic masterpiece won't last forever. Over unimaginable timescales, star formation will fade, and our galaxy will slowly die. The process has already begun. The Milky Way's star-forming gas has been declining for billions of years as much of it has been used up or expelled by supernovas and stellar winds. In about 10 billion years, there will be no fresh gas left to make new stars. Our galaxy will become what astronomers call red and dead, filled only with old, fading stars. The bright blue giants that light up star nurseries today will have long exploded. Stars like our Sun will swell into red giants, shed their outer layers, and end as white dwarfs. The galaxy will grow dimmer and redder as only small, long-lived red dwarfs remain, burning slowly for trillions of years, the last faint embers of starlight. Eventually, even those tiny stars will burn out, leaving behind cold brown dwarf remnants. At the same time, the supermassive black hole at the galaxy's heart will grow in influence, feeding on nearby gas and stars. Those that wander too close will be torn apart by tidal forces, their matter consumed in brilliant flares of light before disappearing forever. Over even longer timescales, dark energy, the mysterious force driving the universe's expansion, will pull the very fabric of space apart. Stars, planets, and black holes will drift away from each other until the galaxy itself unravels. In the farthest future, the remaining black holes will evaporate through Hawking radiation, fading over time periods so vast they're measured in Google years, numbers with more zeros than atoms in the observable universe. When the final black hole vanishes, the Milky Way's existence will end. But perhaps end isn't the right word. The matter and energy that once formed our galaxy will continue to exist, scattered across the cosmos, eventually taking part in new structures, new stars, new galaxies, maybe even new forms of life. The atoms forged in the hearts of our stars, carbon, oxygen, iron, will endure, becoming the building blocks of whatever comes next in the universe's endless story. And as vast as the Milky Way seems, it's just a tiny spark in a much grander cosmic sea. Beyond us lie galactic giants, so massive they make our home look like a cosmic minnow. The largest known galaxy, IC 1101, is a colossal elliptical titan stretching over 5 million light-years across. To put that in perspective, the entire distance between the Milky Way and Andromeda could fit more than 20 times within IC 1101's diameter. It contains 100 trillion stars, about 250 times more massive than our galaxy. If the Milky Way were the size of a basketball, IC 1101 would be larger than a football stadium. And size isn't its only claim to power. Some galaxies shine with the energy of thousands of Milky Ways, fueled by supermassive black holes devouring enormous amounts of gas and dust, blazing beacons in the dark, reminding us of the unimaginable scale and beauty of the universe we inhabit. These incredible objects, known as quasars, can be detected from billions of light years away because they outshine everything else in their cosmic neighborhood. The black holes that power these beacons hold the mass of tens of billions of suns. One of the most extreme examples lies at the center of the Phoenix Cluster, a galaxy forming new stars 500 times faster than the Milky Way. This galactic monster is turning gas into stars so rapidly that it creates several solar masses worth of new stars every single day. At this pace, it could double its stellar population in just a few 100 million years. Then come the galaxy clusters, true gravitational giants containing thousands of individual galaxies. The Coma Cluster alone harbors over 1,000 large galaxies and countless smaller ones, all bound together by dark matter halos holding the mass of 1,000,000 billion suns. These clusters are the largest gravitationally bound structures in the universe. Yet, some of the strangest galactic monsters are those that shouldn't even exist according to our current understanding of cosmic evolution. Astronomers have discovered fully mature, massive galaxies that formed when the universe was less than 1 billion years old. These ancient giants somehow built enormous stellar populations in a fraction of the expected time, defying our theories about how galaxies form and grow. Some galaxies even practice cosmic cannibalism, growing larger by consuming their smaller neighbors. The galaxy M87, for instance, shows signs of having devoured dozens of smaller galaxies over billions of years, amassing a staggering mass equivalent to 6 trillion suns. Our own Milky Way, with its 400 billion stars and graceful spiral arms, is just one small, quiet example in this vast cosmic zoo. We inhabit a relatively calm neighborhood, yet the universe teems with galactic monsters that dwarf anything we can imagine. These colossal giants help us understand where our galaxy fits in the grand hierarchy of cosmic structures. After journeying from our solar system to the farthest reaches of the Milky Way, it's time to zoom out one final time to see where we truly belong in the universe. Our complete cosmic address unfolds like a map of nested structures, each grander than the last. We begin on Earth, orbiting the Sun within our solar system, located inside the local bubble of the Orion Arm in the Milky Way galaxy. But that's only the start. The Milky Way is part of the Local Group, a cluster of over 80 galaxies dominated by the Milky Way, Andromeda and Triangulum. This group spans 10 million light-years and contains roughly 3 trillion stars. The Local Group itself lies on the edge of the Virgo cluster, a massive gathering of more than 2,000 galaxies, about 54 million light-years away. At the heart of this cluster sits the giant elliptical galaxy M87, powered by a 6 billion solar mass black hole. Our Local Group is slowly being pulled toward this cluster by its immense gravity. But even the Virgo cluster is just a small part of something much larger. The Virgo supercluster, also called the Local Supercluster, stretching across 110 million light-years, it contains around 100,000 galaxies, one of the largest coherent structures in the nearby universe. Recent discoveries reveal that our supercluster itself belongs to an even greater structure, Laniakea, meaning immeasurable heaven. This supercluster of superclusters spans over 500 million light-years and holds the mass of 100 million billion suns. At its gravitational center lies the Great Attractor, a mysterious force pulling our entire Local Group toward it at over 1 million miles per hour. But the hierarchy doesn't end there. Laniakea connects to other superclusters through vast filaments of dark matter and galaxies, forming a cosmic web that spans the observable universe. Between these filaments lie enormous voids, cosmic deserts almost empty of galaxies, so vast that light itself takes hundreds of millions of years to cross them. Your full cosmic address reads Earth, Solar System, Local Bubble, Orion Arm, Milky Way Galaxy, Local Group, Virgo Cluster, Local Supercluster, Laniakea Supercluster, Observable Universe. Each level contains countless stars, planets, and perhaps even other forms of life. Understanding our place in this hierarchy reshapes how we see everything. From our quiet solar system to the swirling arms of our galaxy, and outward to the cosmic web itself, we've traced our path from the familiar to the unimaginable. The Milky Way isn't just our home, it's a living, evolving system where matter and energy perform a dance beyond human comprehension. Every atom in your body was forged in ancient stars that lived and died long before our sun existed. You are literally made of galactic recycled material, stellar ash shaped into a being capable of wondering about its own origins. Yet, for all we've discovered, the mysteries only deepen. Dark matter outweighs visible matter 10 to 1, yet we have no idea what it truly is. The supermassive black hole at our galaxy's core warps space and time beyond known physics, and the universe itself appears to be accelerating apart, driven by an unseen dark energy. We live in an age of cosmic discovery unlike any before, detecting gravitational waves, capturing the first images of black hole event horizons, and witnessing the early universe through the James Webb Space Telescope. But amid all this knowledge, one fact remains: we are the only known observers in this grand cosmic theater. On a small blue planet orbiting a middle-aged star, the universe has become aware of itself. The next time you look up at the night sky, remember, you're seeing just the faintest edge of a galactic city filled with more stars than grains of sand on Earth's beaches. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in the hearts of ancient stars. Our journey to the center of the Milky Way shows that we don't just live in the universe. We are the universe, organized into a form capable of understanding itself. In understanding our galaxy, we understand ourselves. And our story? It's only just beginning. Subscribe for more cosmic journeys, because the next revelation might just change how you see the universe and yourself.